Good evening, everyone. So this is our fourth problem solving session. Uh, I'll start with the last previous week's assignment. Our first question was simple. The company needs to evaluate that if the corrosion rate of the metal decreases with time, but they only have one specimen available to make the study. So which other techniques can be employed? So since the TEFL extrapolation is a destructive testing, and you only have one sample, you definitely want to measure linear polarization. If you want to measure the corrosion with time, you can measure corrosion rate of different times, rate if it's decreasing or increasing. So I think this is because of non-destructive method, the linear polarization. That's why it should be good. Mm, Next, second question, I think it's very similar to the question we have done in the second assignment. Here I'm getting slightly different values. 156 amps per meter square instead of 158. Yeah, it's close enough, so you can do it. So let's quickly solve it too. So we're given 1 molar HCl. So the H plus ion concentration is equals to 1 moles per liter. Mm, things we have to assume from the previous the question from assignment, uh, the third assignment, also the second assignment. Sorry. So the zinc reduction potential was given as zinc to the standard reduction potential was given as minus 0.76, and the zinc ion concentration was also given as 10 to the power minus 6. These things are missing here. So anyone who solved the previous assignment would have been able to solve it. But if someone tried this question for the first time, they might have been not confused. And we're given the exchange current density for the zinc at 0.1, and for hydrogen, let's see, 10 to the power minus 4 amps per meter square at the standard meter square, and it's correct. So now to calculate the reduction potential for hydrogen, standard potential is 0.059 divided by 2 log of the time concentration, which is 1. So log of this whole thing becomes 0. So the reduction potential becomes 0. Similarly for zinc, uh, standard reduction potential is 76. So the reaction is zinc plus 2 electrons, zinc minus of 0.5, 0.05, 0.059 divided by 2 is 2 electron log of zinc ion concentration. Activity of zinc metal and electron is 1. So minus 0.76 minus 0.059 divided by 2 log of 1 over 10 to the power minus 6. So this becomes minus 0.76 minus 0.059 to log of this goes up to the power 6. So this is 6. So this becomes minus 0.937. Mm. Uh, Now we know the reaction potential, so we just use the McCaffrey equations. So eta anodic equals to E core minus E Zn reaction potential is equals to uh, 0.1 log of E core divided by 0.1. This is given. The exchange current density for zinc is not zinc. 0.1, and for hydrogen it's given as 10 to the power minus 4. So if you just put the values E core minus 0.9 minus of minus 0.37, this equals to 0.1 log of E core 1 for the cathodic reaction. E core minus 0, so minus 0.1. Therefore, slope is given as beta anodic equals to beta cathodic given as 0.1 volt per decade, right? That's just one. the log of I corrosion by the exchange current density for hydrogen 10 to the power minus 4. If we just so this is our equation 1. This is equation 2. We subtract equation 2 from 1, and we left with 0.937 0.1 log of for 1 minus 0.1 log of 4 10 to the minus 4. This has become log of I core, and if you just add these two things, log sum of logs becomes multiplications I core 1 10 to the minus 4 and multiply both sides by 10, 7.37 log of I core square plus log of 10 to the power 5 and plus 5. So take 2 out. So 2 log of I core plus 5. 9.37 minus 5 divided by 2 goes to log of 4. Just finding out that patient 140 185 1.185 the log of 4 I core equals to 10 to the power 2185. So this value comes out 153.1 amps per meter square. The meter in the centimeter square. If you just substitute this value, in the first second equation, uh, this one, you can get the value of E core. E core equals to minus 0.1 log of, just take this value, give you 10 to the power 2.185 divided by 10 to the power minus 4. Equals to minus 0.1 log of add up 10 to the power 2.185 plus 4 so minus 0.1 into and get the power goes out so 6.185 minus 0.6185 approximately minus 0.62. That was A option. Mm, Third question. Ecore of metal in zero point 0.1 mole sulfuric acid was found as yes. So to there is a need to relate the measured current due to hydrogen evolution on the metal to the applied potential. Following four potentials were selected. Which of them would be correct? Okay. So even second. Yes. No, five. This is your zero. Hydrogen. This is hydrogen. Electron. This is metal. um, Metal plus electron. This is conduction. Electron. UCH. And this is metal plus electron. Using metal. Okay. This is your I core. This is the excitement density for the metal. And your E core. E core we are given as 0 point minus 0.6, and we have 0.1 molar sulfuric acid. So we want to measure the hydrogen evolution. What will happen if we go below to a more negative potential? What will happen is we'll get these 2 points. This is our anodic current, or this is our anodic current, and anodic, and this would be our I cathodic, right? So, and the difference between two, this would be measured in your external circuit, right? So, I cathodic minus I anodic is equal to I measured or I external. So, in this case, remember this is a log scale. So, the difference between these two values would be a log. So, if the gap is large enough, we can say this value is too small compared to this. So, I cathodic would be approximately equal to I external. And this would be our hydrogen evolution, like current for hydrogen evolution. So it's preferable to go down. If we would have gone to the other direction, like for a less negative value, then uh, the anodic current would be higher than the cathodic current. Like much far away, the external current will be measuring would be anodic current. So it's favorable to, if we want to measure the hydrogen evolution, we want to go down actually. And if we wanted to measure the corrosion current, like the rate of corrosion, it would be favorable to go up instead. So that's why we want to go down. So any potential which is V less than minus 0.6 would be the answer. This value is like completely unfeasible, like 605 volts. So I'm not considering it. So these two values would be correct. I hope that makes
Why
sense.
minus 605 volt SHE is incorrect?
Uh, it would be what would uh, I just presume it's maybe it's a typo or something. Such a high current voltage.
But higher the voltage, higher will be the hydrogen evolution will take place in this case also.
Yeah, it will. Uh, will it follow the same? Like, will the diffusion? Will it remain linear? That's what I'm thinking. Maybe the diffusion plays an important role at such a high voltage. So, you get the point.
I
The,
feel that this option was minus 0.605. Due to
yeah,
some error, it has been written as 605. If it was minus 0.605, then at 5 millivolt difference, maybe we can say that the polarization is not enough
yeah,
to
yeah,
generate hydrogen. But with 605, it will generate hydrogen.
yeah. It should, but I don't know. Maybe, yeah, maybe that's a mistake. There's a typo. That's what it is. And maybe the diffusion, those high currents, the diffusion would be limited of the hydrogen mistake. Maybe I don't know what will happen.
But in
Resolution.
that case,
Yeah,
then there should be a mention of
yeah, yeah,
some
yeah. So
oxygen
yeah,
reaction. Then we can say that
and there's diffusion play, yeah, limited. I
actually I
get
have
your point.
marked second,
You
third, and
marked
fourth
all
option. The
three?
second correct, so I haven't got marks in this question. But I feel that 605 also fits into the case. So it's also
Okay. Uh, did you mark the second option?
I have marked second, third, and fourth. So,
Second,
third
third,
and
fourth.
fourth are
Okay.
correct. That we agree.
Yeah, if you just
But
strictly go by this definition, these three should be correct.
if it was 0.605, then we can say that only there is a 5 millivolt difference, and
Yeah,
such a
the
low
difference
difference
would be too
is
small and
too small to generate hydrogen.
yeah.
605, it will generate hydrogen.
Hmm. I can again send them email, ask them to maybe consider both these options as correct. Like,
605 should
BCD,
also be considered as correct.
BCD and the CD both could be considered correct. Yeah, it's a fair argument. I can ask the team, NPTEL guys.
Okay, thanks a lot.
Okay. Next one is a theoretical question. So, which of the following is true with respect to Forbach's diagram? So, Forbach's diagram relates the E and how the the reduction potential, how it relates to the pH of the solution. From the last equation, you get the reduction potential and how it relates to the chain concentration. Okay. So it doesn't work out but for alloys that well if you remember the slide. It's like shortfall. It mostly works for pure metals. And for aqueous, uh, for aqueous solutions only and pure metals. So, and we can use it to predict the metal will corrode in the given in the given pH under the water. So yeah, it is the predict if the metal will corrode at the given pH in potential in water. Otherwise, it doesn't work. Within the influence of fluoride and possible and this, nah, it only relates to the pH. That's right. Yeah, it's correct. Right? Yes, correct. Interesting. Yeah, it gives no information of the kinetics or doesn't give us anything about the rate. It just tells us thermodynamically, yeah, if it will roll or not. Let's see the next three questions. And question 5 to 7. In an alloy development program for seawater application, an audit polarization curve for investing for 5 different alloys listed below. The following table gives us a summary of the parameters such as passivation potential, passivation current, uh, the current density, the limiting current density, for catalytic reaction under stagnant condition. Okay, the limiting current density for catalytic reaction under stagnant condition. Okay, these alloys are expected to be subjected to two different velocities, v2 and the v velocities. Yeah, limiting current density changes to 145 and 200 micrograms per centimeter square. Based on available data, indicate the increasing order or the trend in the correction rate for these alloys. Okay. Now this is a polarization curve for metals which can form passive layers, passive film on the surface. Okay. Just mentioning all the things. So this is our critical current density, IC. This is passivation current density, IP. This is PP, the passivation potential. And so we're given, we have 5 different alloys. Okay. These two have same passivation current density and the critical current density is different. And so is our TPP. So if I just draw these, and then we have limiting current density. So for the cathodic reaction. So since it's talking about flows, we are assuming the it is diffusion limited reaction. So this IL is assuming that after a point it doesn't change. Yeah. And now we just have to determine whether these metals are passivating or not. So if this for the first one, for the this is 115. We just assume Fe. This is 5000. So the IL is much less than my critical. So it will be in the active region, active corrosion region. So it will corrode. The passive layer has been formed. Yeah, the corrosion will take place. And we just have to plot all these 5 plots. So I'll plot these. I'll ignore the post passive region. Suppose this is the first one. Minus 0.1. And we with the least IP first. The least IP is this one. So this is density of 0.5. Okay. Next is 10. Next 8 lines. Okay. So this is minus 0.4. The next one is also similar, but goes a little bit down. The limit and critical density is different. And this is our third sample. And fourth and fifth. This is fourth, fifth, and sixth one. Second one. This and right here. Right here. This is this is the second. This value is 0.2. And the first one is something. This is a, I don't know. Okay. And this is first sample. So this has current density, critical current density of 5000. This is the second one. You have to close to each other. This is the second one, and this is the fifth one. Second one has 150. This is 130. This is 120. And this is 50. Okay, this is point one. And this was 0.5. Okay, so for the first case, in the stagnant conditions, can I change the color? In stagnant condition, also copy this. Okay. So in stagnant condition, it will be something like 14, so somewhere in between. So extend this excess effect to be something like this. Okay, we'll go straight down. It only crosses critically the density of the first, but the third sample. So this for the third sample, it will be in the passive region, and all other four samples, it will be in the active region. So in fact, in those samples, active corrosion will be taking place, and the current density will be all almost similar. It's diffusion limited, so it's vertical and whatever this kind of effects, that would be a current density and the corrosion current density. So um, so I score for the third one would be least, and for all the other samples, I for 1, 2, 4, and 5 would be same since yeah, only this sample reaches the passivation forms of passivation, and passivation is still on the top. So oh, not third one getting confused there. not third, this is fifth one. I just copied from the solution. Confusing myself. Okay. Okay. This is your exchange current density. The diffusion limited current density. So this for sample 5, since it's crossing this 50 micron micro amps per milliliter square. So that's why only fifth sample is getting passivated. IF5 is less than, and for all other samples it's same, almost same. So IF3, IF1 is equal to IF2 is equal to IF4 is equal to IF3 and 4. That's why second answer was correct. Okay. And now if we increase the velocity of the solution of the liquid, yeah, diffusion current limited diffusion limited current density would increase. So here now it's 145. So this was 50, and this was I think 150, right? Yeah, 150. So it's in active region for second, active, and for first, it's in active region. In this region, so active actually, and for this one, it's also active. So since these two are in active region, they have the most, their, they have the highest corrosion rate. So and they would be again almost equal. So I of 1 would be almost equal to I of 2. And for all others, now we have to see the passive wave critic and the the passivation current density IP. This IPLA. So for first sample, I will copy this table again. So we know for the first two samples, it will be in the active region, so highest corrosion. For these three samples, we have to see the passivation, passivation current density. So for these two samples, it's equal. So I4 is equals to I5, and I1, I3 is the lowest. So I3 is lowest, and we have I5 and I4. I4 is equal, and then these two are equal since they're in the active regions, and again they're less than this. But I1 is equals to I2, 1. So that would be the order. So that was
सर मेरा एक ना डाउट है इस क्वेश्चन में, इस सॉल्यूशन में, इसमें मेरे को जैसे अभी जो कैथोडिक कर्व है इसका
हाँ
जो इक्विलिब्रियम पॉइंट है वो हम एनोडिक कर्व के जो ई पैसिव है उससे अधिक मान के चल रहे हैं, पॉजिटिव मान के चल रहे हैं।
हाँ
अगर ये कम रहता है जो इक्विलिब्रियम पोटेंशियल है कैथोडिक कर्व का ई पैसिव से, तो ये इंटरसेक्शन जो है वो पैसिव जोन में ना होकर के एक्टिव जोन में होगा, तो उस केस
इस
में
तरह
कैसे
से
इंटरप्रेट? जी, तो क्योंकि इसका इसका इन्फो क्वेश्चन में दे नहीं रखा है, तो ये कहाँ से
हाँ
चालू हो रहा है कर्व?
फिर खेल जाएगा फिर किसी में पैसे देयर वुड बी नो पैसिवेशन देयर हाँ फिर इन सब में तो पैसिव एक्टिव रीजन में ही है
तो मे भी शायद डिफरेंट ऑर्डर मिलेगा, अगर अगर ये
हाँ
एज्यूम करते हैं तो ये जो ऑर्डर है हो सकता है हमको ऑप्शंस में मिले ही ना।
हाँ ये सही बात है हाँ they should have mentioned it clearly explicitly uh, the the reduction cathodic reduction potential ठीक है तो थर्ड पार्ट में अगेन थर्ड पार्ट में अगेन the limiting current density is 200 it's higher than this so these four are again in passivation region except this one I1 would be highest and then all of these four now we have to judge by these values so I2 is next one then this I4 and I5 are equal and then the least one is I3 again again starting point here लगे तो फिर you will get different values okay okay finally last question again theoretical what happens procedure following is true in case of adding oxidizers to a periodic system and we are assuming it has forms a passive layer so different uh, so it was oxidizer concentration so if you had like Fe plus 3 was added it would have tendency to oxidize they will get reduced like this so at low concentrations as we increase the concentration the current the corrosion would increase okay so initially it would increase okay so corrosion rate initially increases so it's correct it's correct decreases as fast so this is incorrect always increases irrespective of the nature of the layer system this is now if we go even further than this till this point we'll see it will increase since we are in the active region, right? Here would see the passive information. So again, let me this, and if it was a little bit like this, we'll increase it further. Now it wouldn't change. So this is decreasing from this value. So it first increases, then it decreases suddenly to this value. Our passivation current density, IP. This is the critical current density, IC. So it increases first, then decreases, and once we reach the post passive region, it starts to increase again. So this is roughly correct. No effect on the corrosion. This is incorrect. So this is incorrect. Incorrect. Irrespective of the nature of the alloy, if it forms a passive layer, then the behavior changes. The corrosion rate continuously increases for an alloy with active dissolution. So if this alloy doesn't form a passive region, then this would be like a straight line. It will be increasing continuously. So if you increase the concentration, it will keep on increasing. So this one is correct. And initiation decreases for passive wetting alloy. So after a certain point, it starts to increase again. So this is like subset of this. That after increasing it further, it starts to increase again. So that's why these two were correct. Okay. So that was our assignment. I think go over the things from the next lecture. So next three lectures they covered the Borbach diagram, so that it just tells us about how the corrosion behavior will change depending on the pH. Okay. So suppose we have a zinc system. We can write the Nernst equation for this for different reactions that would place. So this is oxidation of the metal, reduction of the metal. The hydroxide can get reduced, or the zinc cation can get reduced. So we have our three Nernst equations. Since in this one there's no HN, it doesn't depend on the actual sign concentration, so it's independent. So in Borbach's diagram, this would appear horizontal since your E doesn't depend on pH. Okay. In this case, we have HN, in the reaction, we have HN rather than 9. So this one, yeah, yeah. So pH is minus of log. So P of H is minus log of HN concentration, where the HN concentration, and if you define it as pH, then you'll get a minus sign there. So that's why it has a negative slope. Okay. So here, if you draw the reduction potential as pH, it will have negative slope. And finally, for the third reaction, again, you have HN concentrations in the HNs in the reaction. So here you'd have both these things, both the pH and the zinc cation concentration. Both these things will affect the standard reduction potential. So depending on different pHs, okay, we have to hide this. What happens in zinc? What are the possible electrochemical reactions which can take place in zinc system? These were the five reactions. At pH above this, and the zinc hydroxide uh, reaction oxidation takes place. So that's how we got these values. pH of 8.5, yeah, 10.8. So we get in this region, since the zinc is getting oxidized, so here you get corrosion. In this region, we have precipitations. We are forming zinc hydroxide on the surface of the zinc, and yeah, immunity if you have below this region, so the zinc is not getting oxidized, so it's immune. And then I think there were some limitations of the Urbex diagram, so it doesn't tell us about anything about the rate. We can identify where in the immunity region where the metal is not getting oxidized, corroded. We can identify the passive region and the active resolution region. However, it doesn't tell anything about the rate, and it's only valid for pure metals and confined for water only, mostly water. Another thing is the pH at the surface is different from the bulk pH since the HN and hydrogen ions are getting consumed to form hydrogen or like uh, hydroxide. In these cases, it's on water or whatever. Like they're taking part in the reaction, so the surface pH, the HN concentration is different from the bulk. So assuming it has the same as the bulk, so let's say right. Then I think there were different methods of different types of corrosion. Those are all theoretical. I think you guys can read Just go over on the lecture and next assignment. So there were few questions in next assignment on corrosion rate. So it's just conversion of uh, some of the questions are just conversion from one unit to another. Like we are given the corrosion rate of iron in terms of GMD. We have to find it in terms of NPY. And they explain what GMD is. I think in the lecture they only covered NPY. NPY is mils per year, which is 1,000th of an inch per year, or we can go millimeter per year. Okay, GMD is grams per square meter per day. Yeah, so we had grams per centimeter square per day. That was weight loss divided by time divided by surface area. If you just take the surface area in meter square, that and if you divide it by the density, so just bring this slide here. GMD is grams per meter square per day. So your weight loss, your time, and the surface area, and if you want to convert it to millimeters per year, here to get it in millimeters per year, you need to divide it by the density. Right? And this is, I think, what's the coming from the time? 87.6. Okay, this is time in hours, so I think that's why this 87.6 is coming from. Because in days, yeah, we can figure it out. Like you just need to divide it by density and get the thickness. From mass per unit time, if you divide it by the surface, the surface area and the density, so you can get what is the decrease in thickness per unit time. And yeah, do the conversion. And I-core, to get the I-core, you can use the DC equation. So weight of metal dilution is if it is given in MPY or millimeter per year, you can use this question to get the value of I4. What else is that? Yeah, this was second, fourth question. We can do this. Next question. Next question. Yeah, again, you have to apply the next equation. Yeah, next one is also simple. Like we just have to apply the next equation, get the values of reduction potential. And then extent of polarization is just e power minus your standard reduction potential. You can get those values and get the polarization to all anodic and cathodic sides. So this is also easy. Yeah. So this in the eighth question, next assignment you're given this is related to the linear polarization plot. So you have the slope, so which relates to the resist R value. From that you can get I core if you know the cathodic and anodic tackle slopes. And if you know I core, then you can use again these formulas to get the corrosion rate in terms of GMD. I think that's it. I'll ask if they can change the solution for this resolution. No, that's all. The third one, if they can allow both BCD and CD. Other than that, yeah, if you guys have any doubt, or else, yeah, if you have any of you guys want to register for the exam, 24th is the deadline. Be careful. It's next Monday, so next time we'll meet. The deadline is after that. So, yeah. Remember this. If you want to register, do it before this the deadline. Okay, then. Yeah. Okay, okay. I'll upload it right after this session. Okay. There is no into transpassive region after passive region. You are referring to this question? Wait. But The statement is correct. The corrosion rate initially increases and then decreases for a precipitating alloy. This behavior is observed in stainless steel. But what if you keep on increasing the oxidizer? I mean, you're talking about concentrated nitric acid, like the examples you took. Mm, check the time. Maybe since it's specific to the stainless steel case, that's why they have chosen this as the correct option. Investigate corrosion rate in Trans-Pacific region. Let me see this. Maybe since it's specific to a specific case, like in case of stainless steel, that's why they are considered it as true. Yeah, close. Corrosion rate. In Trans-Pacific region, water breakdown. Leading all the reactions taking place. Let's see. Settle down the reaction. Yes, that's right. Yeah. Are you talking about water reduction or water oxidation, like OER oxidation?
जैसे ट्रांसपेसिव रीजन में जब जाएंगे तो पोटेंशियल
Uh-huh.
पॉजिटिव जाएगा, तो पोटेंशियल पॉजिटिव जब जाएगा तो चांसेस ये भी हैं कि जो वाटर का स्टेबिलिटी रीजन है ना उसके
हाँ
बाहर
हाँ
चला जाए। तो उस केस में ना वाटर का ब्रेकडाउन होगा, ऑक्सीजन बनेगा, H+
हाँ
आयन बनेगा, इलेक्ट्रॉन लिबरेट
से-
होगा, साथ में
हम्म,
एनोडिक डिसोल्यूशन भी होगा। तो जो पोलराइजेशन मेथड है उसके थ्रू हम कैसे आइडेंटिफाई कर सकते हैं कि हमारा एनोडिक डिसोल्यूशन का इतना कंट्रीब्यूशन है टोटल मेजरमेंट में जो करंट मेजर कर
हम्म।
रहे हैं, और वाटर का जो ब्रेकडाउन हो रहा है उससे जो इलेक्ट्रॉन निकल रहे हैं उसका इतना कंट्रीब्यूशन है। वेट लॉस से तो हम कर सकते हैं, हमने सैंपल निकाला, हमने मेजर कर लिया,
हाँ
बट
हाँ
पोलराइजेशन मेथड से कैसे करेंगे?
पोलराइजेशन से लग रहा है। पोलराइजेशन मतलब में गो बियॉन्ड के ऊपर है नीचे। और यहाँ पे दो रिएक्शन एक साथ हो रही है।
हाँ जी सर, दो रिएक्शन हो रही है। अगर वाटर
हम्म,
स्टेबिलिटी से पोटेंशियल से काफी बाहर चले जाते हैं तो काफी
हम्म।
प्रोमिनेंट इफेक्ट होगा वाटर रिएक्शन का भी।
यस, इसमें एक और करंट ऐड हो जाएगा मे बी। इस पोटेंशियल पे वाटर रिड्यूस होगा, वाटर ऑक्सीडाइज होना स्टार्ट होगा। वहाँ पे विल हैव अनदर करंट। अभी तक आइडिया नहीं है। देख सकता हूँ अगर मिलता है तो उनके कुछ देखते
ठीक है
हैं।
सर।
ठीक है।
सर एक रिक्वेस्ट और था, जैसे जो लास्ट असाइनमेंट में दो क्वेश्चंस में जो उसको आपने बोला था करेक्ट कराने
हाँ
के लिए,
हाँ हाँ,
उसको
वो
सर
मैंने
प्लीज
कल
टेकअप कर
मेल
लीजिए।
भेजा था उनको, अभी तक कुछ रिप्लाई नहीं आया।
अच्छा सर,
मैं एक बार
आज का भी
रिमाइंड
जो
कर।
थर्ड क्वेश्चन है ना सर उसको भी एक बार टेकअप कर लीजिएगा,
हाँ ठीक
तो
है।
कंसिडर हो जाता है।
हाँ ओके, थैंक यू ऑल फॉर टर्निंग। I'll upload this video right away along with the slides. Okay, thank you.